on the computer. All right, we are recording. This is Zoom Day, February 5th, AP Calc 2021, Planet Earth. Who knows? Send it out to the cosmos. Maybe I'm teaching Calc to the aliens. I don't know. If you have a question, I do know how to edit you out. I think your voice is okay. Your likeness is now down in this little window. So I believe I'm abiding all confidentiality issues. So anyway, um, I need my glasses. Zoom notes for today reside in, nope, not there. Back up one. The Zoom notes reside in this little this page attached to Schoology about a minute ago. This is what I'd like to cover today. And I think this is it. Yeah, this should be it. Little talking to you. A little announcement about a derivative quiz next week. And I had a request for a topic question, so I wrote one similar. That's at the top of the page. We've got a couple of integrals that all look the same. And the techniques of integration are pretty much done. Now it's a matter of mastering them. And part of mastering them, besides the mechanics of doing them, is to recognize which one to use and where. And then I have a couple of video clips to show you. A couple of just geeking out on you here. It's when the content of our course has shown up in reasonably popular movies. So let's start with the top of the page here. I received this from Dr. Philgrove. Well, we all did. Administrators get on certain kicks, and that sounds trivial. Certain things bubble to the top of their awareness. And a couple years ago, this was one of the things that bubbled up to him. What is it that we actually give to our students as they come and go through our mathematics program? And you'll notice in there, it doesn't say anything about the unit circle. It doesn't talk about U substitution. It talks to bigger picture type of things. This in theory is what, and this should speak to all levels of students at Cedar Cliff. The kids that take the most basic 3 math classes they can get away with and get their diploma, all the way up to you guys, which are taking ostensibly the toughest math course that a high school can offer. They speak to both demographics, and I think it's worthy to look at, think about, especially number 1. Make sense of never before seen problems and persevere in solving them. I can speak to that, especially with respect to those of you that are taking the AP test. I cannot begin to prepare you for every way they can ask a question. I'm going to talk you through as much as I can and coach you up as much as I can, but that's why your understanding of it is so important. I mean, I teach the lower level courses, and I know what happens on the review days where you give them a set of review questions and they work through it, and you give them the answers, and everyone's you grind through it, and the day of the test you basically give them the review exercise, but you change all the numbers. That's not really the answer to point number 1. Make sense of never before seen problems and persevere in solving them. So that's the challenge as you're looking at yourself in this course, yourself in this life and your education. Please keep in mind that sometimes your teachers don't hold you to these more visionary goals that at least Dr. Philgrove at one time thought was important enough to share with all of us. So that's just food for thought. Next week, we are going to have a new derivatives quiz. I realize a couple of you have not had a chance at taking the first one twice. I will make sure that you have access to that on Monday or Tuesday. Next week's derivative quiz will be Wednesday, Thursday, depending on which cohort you are in. I will write a set of 10 comparably challenging questions. I am inviting you to do the same. How was I going to do this? I'm thinking out loud how I'm going to do this. And maybe by the end of class, I'll have a policy. I want you to write, if you want, I want you to write 10 questions, 10 derivatives. I don't want like textbook definition derivatives. Don't ask me what's the derivative of x squared. Don't bother with those kind. What's the derivative of the sine of x? Don't want that one. I think it should have a cross section of all possible rules. There should be at least one product rule, at least one quotient rule. I think there should be a number of chain rules, and I don't think they got to be ridiculously hard. I'm not looking to trip you guys up when I gave these series of quizzes over the last couple classes. My goal was to build a competency with you guys so that we can successfully move forward in the class. So if you write it, here's my thought right now, is if you write it and give me a 100% accurate answer key, I will count that as a 10, and whatever you get on Tuesday, Thursday, I will average that 10 that you give to me, I will average that with whatever you get on Tuesday, Thursday. So if you think, well, I'm going to get a 10 anyway, then don't bother writing one. All right. But if you think you want to maybe write out get a little insurance policy on this, and you want, hey, I want that 10. So if I get a 4, then, at least the 10 plus the 4 averages out to a 7 out of 10. Now, here's the stipulations. Your accuracy must be accurate, and I don't want to be doing extra work with your version of a quiz. If you're going to write this, I want a Word document. So you got to know how to put equations into a Word document. I'm looking for 10. They have to be sufficiently challenging, on a par with what we've been doing, and cross-section of all types of derivatives. I mean, you can't possibly ask one of every type, so make sure you give me a logarithm. Make sure you have an exponential. Make sure you have a inverse tangent or one of those inverse trig functions. All right. So there you go. If you have any questions, well, I got to have this before Wednesday, Thursday, so I will need it Monday or Tuesday at the latest. And now on to the festivities continue. When you do your topic questions, which are today at 10:45, like they have been for the last 20 months or however long we've been doing this. No excuse for getting timed out. All right, get this done. There's nothing to stop you from having it done already. But 10:45, the carriage will turn into a pumpkin, and you will not be able to do the topic questions. Don't forget, there are also videos that are due that coincide with these topic questions. Anyway, in your topic questions, you might see one that looks something like this. And it is literally worded just like that. Let f be a differentiable function such that the integral of f of x times the cosine of 3x dx is, and then they have f of x, the sine of 3x over 3 minus the integral of f of x sine of 3x dx. Give a possible expression for f of x. Well, first thing you should recognize is that this thing is written in an integration by parts kind of technique. So my advice for you to solve this one is to get into pen mode here. Ignore this for now, ignore the right side for now, and just focus on the left side and do that. Set it up as if you were doing integration by parts. I'm going to be quiet for 30 seconds while I do this. While I'm doing this, I would like you to start on your own. I don't want you to just hang out and wait for me to write an answer and then copy down what I write. Remember what I was talking about with Phil Grove's transfer goals? You copying down my work is not learning. All right, so 30 seconds, start now, set it up. Okay, that's how your setup should look. Then you've got to fill this in by taking the derivative of the u and by integrating the dv. Let me switch colors to highlight. And why did I jam myself on the right side of the screen? I don't know. The du is, okay, I'm going to stop talking as you guys do this. That integral of the cosine of 3x. We were talking about this yesterday and on Wednesday. This is one of those where you sure, go ahead, do the u substitution. U equals 3x, go for it. But you should be looking at trying to see the shortcut of how to do this integral. Okay, until you get the hang of it, try taking the derivative of that. 1/3 the sine of 3x is 1/3 the cosine of 3x times 3, which sure enough is the cosine of 3x. So let's assemble this using integration by parts. There you go. I think that's as far as you can go. Now what I want to do is here's what I believe a strategy to solving and answering this question is let's match up our attempt at integration by parts with the question itself. They're saying that the integral is f of x 1/3 sine 3x minus the integral 4x sine of 3x dx. Okay, and this is rhetorical, do you have enough information to take a stab at what f of x was? And your strategy is just start matching things up. Well, first of all, notice we got this sine of 3x here, matches up with that sine of 3x there, right? And this dx matches up with that dx. So really what we're looking at, in order to transfer from the blue line to the green line, what we've got to have is somehow f prime of x times 1/3 has to somehow find its way into becoming 4x. Okay, well, f prime of x is equal to 12x. A possible value of f of x is, let's integrate both sides. F of x could be 12x squared over 2, or 6x squared. And that is a possible value. It could also be 6x squared plus 1. It could be 6x squared plus 12. It could be 6x squared plus 120. That's the whole deal with the plus c thing. But the bottom line is that is how I would approach answering that particular topic question. Take the integral that they give you, do your own version of integration by parts based on what they gave you, and then match up your integration by parts with what they provide you and see what you can match up to answer the question. All right? All right. Boom. Bada bing. On to the next. All right. Integrate the following. Okay, what I want you to see is there is remarkable similarity between these things, and how are you going to reconfigure them so that you can successfully integrate? These are all candidates for integration. You should be able to do each of them. I'll give you phone out, set it for 1 minute. Here's the hint. They're all inverse tangents, and what else was I going to say? Wait, are they? Yes, they're all inverse tangents. And I would venture to say two of them are walk in the park easy, right? So let me see, where's my timer here? 1 minute. Okay, I will not talk for 1 minute. All right, that's time. The integration for each of these, the one in red, is on point with the rule. That integral is 9 tan inverse of x. Let's see. All right. The second one, you've got to do a u substitution. Hopefully you recognize that u is equal to 3x. In order to do my shortcut, what you would need is you would need a factor of 3 in order to execute the integral. And to balance that factor of 3 that I just included, you'd have to pay for it, if you will, with a 1/3. I've effectively multiplied this thing by 1. And the result is we get an integral of 1/3 tangent inverse of 3x plus c. That's the second one. And finally, the third one. Hopefully you recognize, again, I told you all these were all tangent inverses. What you need in order to, if you do a u substitution, purple here, your u substitution would be along the lines of u equals x over 3. If you proceed with that u substitution process, well, here's what you would end up if you didn't. You'd, in order to execute this integral using an inverse tangent rule, you need a 1/3 in here. And you've got to pay for that by multiplying by 3. And what you're going to end up with is 1/3 tangent inverse of x over 3 plus c. All right. And if you don't like my shortcut, then pursue one of these two u substitution methods. What you're working towards getting is, again, you want to set yourself up so that you can do an inverse tangent rule for integration. And your answer will be there, there, or there. All right? Okay, I got 3 more that are looking a little bit like the 3 I just did. Again, what we're working towards, guys, is we're working towards not just the technical proficiency of integrating. We're looking towards the subtlety of which method to apply with a given integral. And part of that is going to come from experience. I talked about the rabbit holes or the dead ends, and you've got to just recognize sometimes you might do nothing wrong. You might do a u substitution. You might have applied a trig identity. There's a bunch of things you could have done, and you still can't integrate. And you just, I know this, I don't mean to sound unsympathetic, but sometimes you have to know when you've hit a dead end and try something else. All right. Or ask me, part of what's going to happen is you're going to develop an experience if you practice this, if you stick with it, and if you practice it. All right. Okay. So clear pen mode. And I think I got 3 more. Yeah, here they are down there. They all have an x squared minus 1 in them. So that's, I know we just came off of doing 3 inverse tangents. These are not eligible for inverse tangent because I got an x squared, and in the denominator, I need an x squared plus 1. And if you try factoring out a -1, then you're going to have a negative x squared plus 1. You can't get rid of that one negative sign. So you're kind of stuck here. And you got to find a solution other than inverse trig. So let me give you 30 seconds. I want you to come up with a strategy for each one of these 3. As I look at them, I think the one in the middle is, I think, the easiest. You hopefully are seeing that you can do that one in the middle in your head. All right. The one on the left and the one on the right, it's going to take a little bit of writing stuff down. So here's a minute. It's on. Go. Those are what you want for your 3 strategies for this. I don't know why I didn't enlarge this before I erased everything. They're kind of tough to see. Sorry. The middle one, we've got the integral of x times x squared minus 1 dx. You recognize that you want to do a natural log on that, so it means you need a u equals x squared minus 1. Why not? Du dx equals 2x. Du over 2x equals dx. And in all of its glory, here is the u substitution. Let me switch colors here. This would be what we've got to substitute is we've got an x over u times du over 2x, which becomes 1/2 the integral of 1 over u du, which is 1/2 the ln of u plus c, which getting out of that u variable is 1/2 the ln. Oops, don't forget those absolute values. X squared minus 1 plus c. All right, that is not how I would have done it. How I would have done this is I would recognize, where we would be the same is I recognize I want to do a natural log. I see the argument of that natural log. I recognize that I need a 2x to make it happen. So I have the x, I need the 2. I got to pay for that 2. I got to balance out the whole thing by multiplying by 1/2. And from there, I go 1/2 the ln x squared minus 1 plus c. Okay, so that's how I would do the one down the middle. The one on the sides, we've been doing partial fractions, so please set that up. Notice x squared minus 1 does factor. What I'm going to do is I'm going to make this a little bit bigger, so take your shot at this while here, let me just, I'm going to make this bigger so I can do the one on the left and the one on the right. So you go do. Let's say you want to set up your partial fractions. I'm skipping a step here, but we've talked about it in class. You should know that the next step is this. Basically, what you're doing is you're making steps to add the a over x plus 1 and the b over x minus 1. You want to add those together. In order to add those fractions, you have to have common denominators. So the fraction with the a in the numerator, you're multiplying it by x minus 1 over x minus 1. And the one with the b in the numerator, you're multiplying that by x plus 1 over x plus 1. And then all we're doing is we're focusing on the numerators of each of the terms in the equation. So we end up with 1 equals a times x minus 1 plus b times x plus 1. Now what you want to do is you want to be clever about picking some x's that get rid of either the a or the b so that you can figure out the other one that's left. So let x equal 1. What you end up with? End up with that, and b equals 1/2. All right, now let x equal -1. And we've got a equals -1/2. So what that leads us towards is our integral is this. We've got -1/2 over, okay, that's the a value, over x plus 1. And then we've got our b is 1/2 over x minus 1. And again, notice we have not really done any calculus yet. All you've done is algebraic preparation so that you can finish an integration by doing calculus. So our close for this is that, I'll tell you what, why don't you finish this and see if you can write down what you think is the best possible multiple choice answer you would likely see on a test. Okay, so integrate as best you can, and basically it's code for simplify. Sorry, Eric, I'm asking you to simplify. Cardinal sin. Murphy never asks us to simplify. Okay, this time, simplify. Switch colors here. go purple. That would be a really awesome free response answer. Leave it like that. However, that's not how multiple choice answer is going to look. Chances are um, you're going to want to switch these two terms around, and it's going to be written as the, oh, shh, quiet, just right. That's supposed to be a plus C at the end. Didn't plan out my spacing as usual. If we factor out a 1/2 from this, you could have done a lot of this in your head, I would suspect. If you factor out a 1/2, you've got the difference of two logarithms. Remember, if you have the ln of A minus the ln of B, that's equal to the ln of A over B. So applying that property of logarithms to our integral, our antiderivative, and that, I believe, is what you would see as the most likely multiple choice. I mean, this is correct, this first line of purple that we have, but I don't think that you would ever, I know the College Board well enough that I think this is probably what they would put as their answer. Right? So let me give a little space. Why don't you take a shot at that long division that we've got? We've got the integral of x squared over this quantity x squared minus 1. What you're looking at is this is a rational expression, the integrand is, and the degree of the numerator is greater than or equal to the degree of the denominator. So this is a candidate for long division. All right, have at it. I'm going to try to clean up my workspace here. Whenever you have polynomials, the dividend, it's a good idea to put space holders in so you have all powers of x. It's not needed in this one, but it's just a good habit to get into. So what we're looking for is what value do we need in order for x squared? What value do we need to multiply x squared by in order to get x squared? Well, that's just 1. So what we'll do is 1 times the x squared minus 1 is x squared minus 1. And that quantity is going to be subtracted away. So we end up with 0 x squareds, 0 x's, and we're subtracting a -1. So we've got plus 1, which is our remainder. So what we've got is this becomes 1 plus 1 over x squared minus 1. Okay, and we just did that one. So our integral for this, hey, it's Friday, cut us a break and we're done early, yes. So the integral of this, okay, don't forget the 1 at the beginning of this. So the integral of 1 is x plus, then the integral of the second term here. We've already done. So we got 1 plus 1/2 the ln x minus 1 over x plus 1 plus c. All right. So embedded in that long division, there was a partial fractions that was waiting for us on the other side. All right. Okay. Yeah, I think that's what I wanted to accomplish today. Okay, I'm going to show you a couple movie clips. Do you guys have any questions at all? Okay.
Mr. Murphy,
Yeah.
for that, if we make our own quiz, you said we have to do it on a Word document.
Yeah, because I don't want to. Okay, let's say you write up a really awesome 10-question quiz. Then it falls on me to type it up so that I can make copies and all that. And I'm not going to do that. So if you
Okay,
want,
and then do we just share it with you from Word?
yeah, however you can get it to me. And I may or may not choose your quiz. If I get 21 quizzes, I'm going to pick a couple. All right. I don't know. But if
But
you
we'll still
submit,
get the
yes,
the extra 10
if
points.
you submit a quiz to me and you have a 100% accurate answer key, then I will give you that sort of. We'll average 10 to whatever you get on the actual quiz you take. All right.
Okay, thank you.
You're welcome. Okay. So, movie clips. Tabular integration. I don't teach this. It is in the book. Basically, it looks like this. So suppose you have an integral of x to the 10th times e to the x dx. Right? Okay, using that logarithms, inverse trig, algebraic, trig, and exponential. This is a candidate where you would use the algebraic term as your u, and your first iteration would be u equals x to the 10th, and the dv would choose as e to the x dx, and you'd have 10x to the 9th dx. And this would be e to the x. And first iteration, you've got e to the x times x to the 10th minus the integral of 10 x to the 9th times e to the x dx. Okay, so you've done one iteration that's got you from x to the 10th to x to the 9th. Then you'd have to do another iteration to get to x to the 8th. And you'd have to do another one to get to x to the 7th. And I hope you can appreciate it's an absolute nightmare. There's a technique, I hate calling it, it's a variant on integration by parts. It's called tabular integration. It is my opinion that you guys have enough things to do. I think it's a bit gimmicky. It is in your textbook if you want to look up tabular integration. There's basically it uses the patterns of the U and changing of signs on, look it up. I have a hard time believing that the College Board would give you that as a question, this thing, as a question and expect you to do tabular integration on that. That's why I don't teach it. If you're so inclined, knock yourself out. If you're so inclined and you still don't understand it, I will answer any questions, but this really is as much class time as I want to spend on tabular integration. It is a variant or a niche of integration by parts. And if you've ever seen a movie called Stand and Deliver, it's a calculus movie. James Edward Olmos plays the teacher. Lou Diamond Phillips is one of the students. It is based on a true story. And James Edward Olmos is, I think he works in the computer field. He wants to do more with his life and decides he wants to be a teacher. So he goes into one of his neighborhood schools, which is a rough school in East LA, I believe. And all he can do at first is just teach the kids how to add fractions. And he struggles with that. And he decides that maybe the reason the kids aren't doing good is because they have such low expectations of them to start with. And they say, well, what do you think we should do about it? And he says, well, why don't we teach them calculus? And they laugh at him, but they let him try. So he teaches calculus. And this particular scene, this is his class, and they're working on tabular integration. And I just wanted you to see it. So here it is. I hope I get this right. I have to watch a commercial.
Mm-mm. Try the shortcut. This is easy. Baby stuff. We're Boy Scouts.
Well, my mind don't work this way.
Tic-tac-toe. It's a piece of cake upside down. Watch for the green light.
I've been with you guys 2 years. Everybody knows I'm the dumbest. I can't handle calculus. These guys have a better chance of making the AP test without me. Don't laugh.
How could we laugh? You're breaking our hearts.
Don't do this, Kimo.
How noble. To sacrifice himself for the benefit of the team. Do you have the ganas? Do you have the desire?
Yes, I have the ganas.
Do you want me to do it for you?
Yes.
You're supposed to say no. Well, I'm going to have to get tough. Bullets are going to have to start flying. We're going to have to work right through Christmas break, okay?
That's Lou Diamond Phillips. He's a pretty big actor in the day.
The counselor was just here looking for you. Something about some cosmetology classes. He says there's 3 different levels. One.
Did he just put up 4 fingers and say 3 different levels? That's something I would do. Hey, this is not the most politically correct little put down that he goes here. So apologies. It's a dated movie.
For boys, 1 for girls, and 1 for I don't know what kind. Why don't you go find out?
Okay, well, please listen, man. It's cool. My grandmother.
Clock out. Game's over. You lose.
You never listen to nobody, man. Te crees al más chingón.
Adios. Why don't you send me some postcards or call me on the telephone. Let me know how you're doing. We love you.
You sabe this, cabrón, huh?
I think that guy's got a bigger problem than you. Tick, tack.
Okay, I think the original integral that they did was x squared times the sine of x. You can see it right over, you can see it over his left shoulder. And he's actually doing this tabular integration, which in the left column, he takes x squared and then 2x and then 2 and then 0. And in the middle column, he just takes derivatives of the sine of x. And I think there's a sign change in there. Again, it's a bit gimmicky, but it's a thing. So
Simple.
Simple. There you go. It's simple. All right. The other thing I had for you was Euler's method. I must have seen Hidden Figures about 5 or 6 times, and it was only in the last time that you barely hear it, but they mention Euler's method. You can link on that, or I think I've already found it on YouTube. Let me see if I can, where is it? Euler's method. Okay, here it is. And here we go.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. We can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method.
Yes,
That's ancient.
but it works. It works numerically.
That's it.
Let's type it up.
All right, there you go. And I'm at a break. I think we're a little early as far as ending class goes. If you guys have any questions, I'm available to you. Otherwise, again, you get the topic questions. Make sure you watch the videos. And there are a couple of ebook assignments waiting for you on Sunday. All right. You're good to go. All right. I'm going to dismiss unless otherwise. Bye, everybody.